Okay, well, it's a great pleasure to welcome Anna Rettoria from Trinity College here in Dublin. She is with us virtually, even though we're only a 15-minute walk apart, but which is fine. We were she's going to tell us about constructing new solutions of the Yang-Baxter equation. Thank you very much, Anna, I will hand over to you.
Thank you very much. Thank you very much for the invitation. I'm sorry not to be there. I have another meeting not long after this, so I had to. That's
okay. No,
but I hope I have the chance in the future.
Please come and visit us. Yes.
Yeah. So I will talk about this work I have been doing with my collaborators at Trinity. So with Marius, Chiara, Anton, and Paul. And it's about integrability. It's about to construct new integrable models. And the idea of the talk is to start with some introduction, what is integrable models, what is Yang-Baxter is, and then explain which method we are using to find these solutions, and apply some specific type of models with SU2 plus SU2 symmetry. And then a second application is for these deformations of ADS. So integrable models, as I will say a bit more later, they appear in many places. So you can kind of use them to understand things in many different places. Sometimes even the same model, like Hubbard model, for example, appears in condensed matter in ADS-CFT. So they're quite interesting, and I'd like to tell you a bit about them. So this is idea, more or less how the talk is organized. And at the end, I'll give some conclusions and further developments. And please, I don't know how you usually do, but for me, like if you want to interrupt at any time, it's fine. I'll be very happy. And so there are these models that they have like a very high amount of symmetry. And as a consequence, they have many conserved charges. Usually in this way, we think about these things. We associate the first charge with momenta, the second with the Hamiltonian, and then you keep going. But you can have a huge amount of them, even infinite amount of them, depending on what you're doing. And if they commute, if these charges all commute, you can say you have an integrable model. It's a way to define an integrable model if you have this tower of conserved charges which commute. And we usually associate the second with the Hamiltonian. As I said, I repeated these twice already. It will be very important in the method. So, yep. But these models, they have so much symmetry that they are very constrained. So you can solve them. So they many times can be used as toy models to understand many things, and because you can completely solve them. They have applications in condensed matter, for example, in magnetism and superconductivity. This Heisenberg spin chain is a toy model of magnetism, for example. Potts model and Hubbard in superconductivity. But they also have applications in ADS-CFT. This is a bit more recent, and you can associate like ADS-5. It's related with this Hubbard model, but ADS-3 is some kind of XXZ model. And ADS2 as some XYZ. I'll talk a bit more about this type of model at the end of the talk. But when I say that we can solve them, what I mean is that there are lots of techniques were developed along the years to deal with this type of model. There are many types of back ansatz and some other techniques that quantum spectral curve, for example, that's very modern. And with these techniques, we usually can solve the model. Not necessarily you have an analytic solution. Sometimes you need to go numeric, but you can kind of, you can say a lot. You can say much more than if the model was not integrable. So it's useful to know if your model is integrable. Like if you take a model, like you take a Hamiltonian, and you want to know if this Hamiltonian, like if you know that this Hamiltonian is integrable, you automatically have like a whole set of techniques you can use to deal with this model that you will not have otherwise. So our idea to find new integrable models was more because like this, I think is the main reason, is like you can, if you know that a model is integrable, you can do a lot with them. So in principle, you have many new things at your disposal. But because there are so many conserved charges, these models, they have some things like what can happen or not on them. It's very well kind of defined. So if you think in a scattering of 3 particles in 2D, for example, because of the amount of these conserved charges, you have no particle production. So the number of particles that at the beginning and the end of the scattering is the same. The set of initial and final momenta is the same. And this 3 to 3 particle scattering, it factorizes in a sequence of 2 to 2 particle scatterings. So, and this happens in a very specific way. So we are in 2D here. So if you have 3 particles scattering, integrability means that you can scatter them in 2 ways. You can have this factorized scattering of 2 to 2 particles. So, but it can happen in 2 ways, and they have to be equivalent. So this statement is this Yang-Baxter equation. It means that if you scatter particle 1 and 2 first, then 1 and 3, and then 2 and 3, you should get the same result as scattering the particles 2 and 3, then 1 and 3, and then 1 and 2. So this is what Yang-Baxter basically says. And these objects called R-matrix, we can, it's directly related to the scattering matrix for this type of model. And you usually think of U and V as the rapidity, like so as rapidities are of your particles. You can think of U and V as the rapidities, or it's related with momenta, depending how you are thinking. Yeah. So you can think this as scattering, but you can also think of the Yang-Baxter as some like the R-matrix as some mathematical object that satisfies that equation. You, in principle, you can treat these as a problem of solving that equation without knowing anything about scattering, or like, so you can think as the R-matrix as just some mathematical object depending on 2 variables, which acts on 2 vector spaces and maps 2 vector spaces into 2 vector spaces. And this is more what we do in the first part of the talk. In the second part of the talk, we'll talk quickly a bit about scattering, but for the method, we can think mostly, we can just treat this as a function of 2 variables. And as I said, like, it doesn't need to be only think in terms of scattering. You can think, for example, in this 1D spin chains. This is very well studied for many models. And you can also think as a scattering in this sense, but you don't have to as well. And this is one place where it appears a lot, is Yang-Baxter. And the point is that when I say that we are finding new integrable models or new solutions, like I just mean new R-matrices, because once you have the R-matrix, you kind of have everything. If you have the R-matrix, you can construct all your charges, you can apply most of those techniques, and you are sure your model is integrable. So if you have an R-matrix satisfying Yang-Baxter equation, it's integrable, and all the techniques are available to you. But there are many types of there are many possibilities for the R-matrix, and method I will introduce for you. We need an object called boost operator to do it, and this boost operator is defined for objects that satisfy this equation, like they are called regular. When you put the two spectral parameters equal, you have to recover permutation, the permutation operator. Permutation just means that if you act on 2 vectors, like if you have a vector on site 1 and vector on site 2, you can switch them by acting with this permutation operator. So if this is satisfied, it also means in your spin chain, so when you construct the Hamiltonian of your spin chain, you put particles in each side. It means like the consequence of having this this regularity property is that you have what is called the nearest neighbor interaction, which means that one side only sees the one in its right and the one in its left side. You just don't see, it doesn't see interactions that are long range, you just see the short range. So the models we are, the R-matrices we are finding are matrices that are related to nearest neighbor Hamiltonian. So this will be the type of model we will be interested.
Sorry,
Yes.
I'm not quite sure I understand what your notation here. When you have R of U being P, but and you have P1, 2 acting on, these are different P.
So,
because it's supposed to act on the same quantity, but P still acts. I'm not sure what the meaning of P is in this case. It's just a notation.
Yeah, it's just notation. It's just that P, P is an object that acts on two vector spaces.
Exactly,
so
yes.
It usually uses two sides, right? And when you have V1 cross V2, you have two sides. So this object has the same. Can you see this cursor?
Yes, yes, we can see it. Yes.
Yeah. So when you have V1 cross V2, for example, let's say this it's a vector space of dimension 2. You just have two vectors of like here you have like a two-dimensional vector, a two-dimensional vector. When you do these, you have a four-dimensional vector, right? And your P acts on 2 as well, so it has it's a 4x4 matrix acting on on a four-dimensional vector. So it gives you another four-dimensional vector. So these 1 and 2 are just indices so you know which ones are acting. I should have been more clear about. I should have written something, but these indices only means that this P acts non-trivially on site 1 and 2. So if you had more vectors here, and you had P12, P12 would act on the first two, and it would act as identity on the rest. So these indices just means that it's non-trivial on sites 1 and 2, and so.
And you are extracting P by some projection, is it, on the left-hand side? Yeah. When R is acting on U.
This is just a definition, like P is the object.
No, it's the left-hand side that I'm concerned about.
Oh, these?
U acting on P.
Oh, these?
Or giving P.
Oh, this is just like you have some R-matrix. You have some matrix, in principle, can be ugly, can be whatever, but satisfies Yang-Baxter. If you put V equals to U, you get a matrix that is exactly the matrix that defines P. Because P is a very well-defined matrix. Let me connect my my tablet, and then I can write. Just a second. No, I don't know what it is. Oh, it's here. Sorry, let me connect because then it's easier. I should have done this. Yeah, when you try to do things fast, then you don't even manage to connect. Let me. So here. Can you see?
Yeah.
So
can I ask you a question? Sorry. You generally this piece you are getting, they will give the braid group, not the permutation group. Why? It will have the braiding relation. That is, P12, P2, 3, P13 will be equal to the other. So there's a braiding.
No. It should be P12, P23, P12 is P23, P12, P23. No, but over here, this is permutation operator. This is not the braid operator. So I think she's trying to get XXX chain. She wants to get the she wants to get the XXX chain from this.
No, so the issue I want to ask is, to define this, you need a coproduct on the original algebra. What is it?
Oh, not like depend what you want to do. Like at this point, I don't have anything more, anything deeper. I'm just really like let's think. How do I erase here? Yeah, it's simpler. It's just for example, if you have let's say our vector space is C2. This P is just, oops. It's really like I'm just choosing a representation here just to. This is it's a much simpler statement. We are not yet in the braid groups or coproducts or anything deeper. It's really, so if you act with P in something that you had like, I don't know, up, down. These will invert. So if you choose a representation for these, for example, 1, 0, 0, 1, this is really, is just a 0, 1. If you act with P here on this object, you have to multiply this matrix here, and it will give you only the third here. If you look, it will give you 0, 0, 1, 0, which is 0, 1. So it really inverts. It's just, I'm just saying. And then when I make this statement on the left, it's if you have like you can have many objects satisfying these, but one example is XXX that was mentioned.
So this is not like half algebra.
No, not yet. No. You don't, like, in principle, you can think as half algebra. Unless when you have a specific R, if you have a specific R like a XXZ or some trigonometric model, you can think in terms of quantum groups and half algebra and all that. But at this point, I'm just making the statement that I want models where the R-matrix reduced to this type of thing.
Okay.
Maybe you can prove something from quantum groups in this sense, but it's not what I at this point. So if you take this model, for example, and you put U to 0, or this is a simple one. So sorry, this is I don't have a quick example of some. I don't know. Usually, you can think as these when U and U are equal, because usually for XXZ you can write these. You can write an R that depends on U minus V. So when you put them equal, you get a 0 here. So if you put 0, you get I times P here. If you get R of 0 is 1, 0, 1, 1. It's really P. Yeah, this is all I'm saying. I'm just saying that I'm interested in models which have these properties. It's nothing deeper, or I don't know if it's
okay. No, I understand now. I think I didn't realize that you and U were your parameters.
Yeah, because fine. R usually depends on two
parameters. Yeah, no, I have it now. That's fine. Thanks. Yeah, and you're just yeah. I was lost in your notation. Sorry.
Yeah, no, but I should have also explained better, because it will also help in the next. But I didn't say what those indices in Yang-Baxter. I said in terms of scattering what they meant, but what they meant mathematically, I didn't say. So
I think it's clear now. So thanks. That's very good.
Yeah. So. Yeah, so, but please, you can ask if it's not clear, please ask again, because, yeah. So so we want this regularity property. So, and for this type of system, you can kind of define the density Hamiltonian as the derivative of the R-matrix. And then you send V to U and multiply by this P. So this is your Hamiltonian. For objects that satisfy that property, you can always define the Hamiltonian in this way. The density Hamiltonian. So, but there is a very important distinction here, and this is related with the two parameters. Like, you have two types of R-matrices. One that's called the difference form, and for these, when U and you can for this type, if you have R of U and V, you can write as the R of the difference. So X, all these are here. And then if you ask U going to V like I did before, this becomes R of 0. That's what I mentioned. And a huge amount of models is known like that satisfy this type of relation. So most of the known models are here. And a consequence of this is that the Hamiltonian does not depend on the spectral parameter, because again, because it's written as the difference. When you compute the Hamiltonian here, you have to send U to 0, because send V to U is the same as if you have only one parameter. It means that you send it to, yeah. If you send, it's actually, you can see from here, if you derivate with respect to one of them and you send the other, yeah, you have the Hamiltonian that will not depend in any parameter, because the two parameters become the same and they kind of cancel when you have. So it doesn't depend on any parameter, any spectral parameter. The Hamiltonian is a constant Hamiltonian in the sense of it doesn't depend on the rapidity. You can have some like constants there, but it will not depend on the rapidity. But there is another one that's called non-difference form, where you cannot write as the difference. This is very important, but very few models are known of this type. So Hubbard model is the most famous example, and then all the ADS ones are here. But you cannot write as the difference. But because you cannot write as the difference, the Hamiltonian does depend on this parameter. So if you have a Hamiltonian that's integrable in the sense that it came from an R-matrix of this type, like you can still get by this equation, the Hamiltonian, it will depend on a parameter and it will be integrable for any value of that parameter.
The Hubbard model is in one dimension, right?
Sorry?
What dimension?
One dimension.
One dimension.
Yes.
This is the problem that Lieb solved. Lieb had an exact solution of the one-dimensional Hubbard model.
Yes. Yes. So yeah, and yeah, Hubbard model is integrable, and yeah, it was by Lieb. Yeah, exactly. Yes. This is so this is very important, but it's very rare, kind of. Yeah, they're not. Yang-Baxter was not solved in general for this type of model. Okay, it was not solved in general for almost anything, but it's much rare. It's very rare to find models of this type, and I'll explain why. What's harder about it. But this is an important distinction. So the examples I will show, like this SU2 plus SU2 that I will show first, will be in the first class, and the ones in ADS will be in the second. And I will explain what changes in the method and what you can do or not, depending on how you solve it.
Sorry, what is the part in the definition of the Hamiltonian?
Sorry, it's hard to understand you. What about Hamiltonian?
Your definition of the Hamiltonian. You have R, but is that a time derivative, or is your R depending on T in addition to U and V?
And
sorry, there is something going on the sound. I just cannot distinguish.
He's asking about your definition of the Hamiltonian and R in particular. I think he may be asking about the dot.
Oh, it's the derivative of respect with the first parameter, for example. You can define as the definition, if the dot is a derivative, the derivative with respect to u, but and this is equal to minus the definition of if you derive with respect to v. It doesn't matter much, it's just an overall.
Since you have, for example, Hubbard model or something, when you have two parameters, I don't know what it should be in that case.
I'm still not.
Sure, he was confused as to what it can mean when you have a two-parameter R-matrix. Is your definition is valid for both the difference R-matrix and the non-difference R-matrix? This will give you the Hamiltonian.
Yeah.
Or is it just simply the difference R-matrix that you get the Hamiltonian from your permutation operator and your
these
R dot?
Yeah, so if it satisfies these, it's simpler. It reduces from that, but it's simpler. It's just P. Yeah, it's there is only one U basically, because U minus V you can redefine as U, and then you send U to 0 at the end. So this is what happens in this case.
Yes, I think the confusion was in the second case.
In the
non-difference.
Yes, so the second case is so you can either do this, but this is or you do minus and you send V to U or U to V. It doesn't matter, you depend on one parameter at the end, but yeah, this is basically one is minus the other usually. But
and what is guaranteeing that? And what is guaranteeing that one is minus the other? Because it's clear when you have the difference case, but it's not so clear in the general case.
Actually, no, I'm not sure. Actually, if this is, I think this is true for. I think this was more something we saw in the models we found. That's really something in general. Maybe I should. I'm. No, I think this is general. I don't remember the argument. I have to think. I don't remember the argument, but we usually like most of the times we just use these and that's it. But it's just we found a specific class of models, and then for them you can. Okay, the honest answer is that I don't remember. I have to think. I don't remember. But
okay, did we answer your question, Werner? Did we get the question across, Werner?
Thanks. Yeah, fine.
Okay, that's fine. We can return to it in the discussion.
Yes. Okay. Because I can think a bit, but I think now it will take me a bit. I have to. Yes. Yeah, so this notation also I didn't explain before, but in just thinking about the notation in terms of R as a mathematical object, you basically have. Let me draw here. Yeah, so you can think as this Yang-Baxter acting on 3 spaces, and then R12. It's R cross identity, R23, it's identity cross R, And 1, 3, you use the permutation operator to. So this is what means here. So you can really choose a representation or do something with matrices, and you can manipulate these objects because you can, you know, this. So let me erase because Zoom just keeps in the next slides the same. So it just, this sentence will appear everywhere. But this is the Yang-Baxter. So just talking about if you try to solve Yang-Baxter without much trying some specific technique, if you just like, you see this equation for the first time and think, oh, let me choose an ansatz and solve it. Let's say you choose the simplest, like this, like 2-dimensional vector spaces. So you have 4x4 R's. You have in principle 16 unknowns, and then you don't know yet. You just put here. You'll be in a huge trouble, like because if you see each R depends on 2 variables, and Yang-Baxter itself depends on 3. So you kind of have it will be very hard to solve. You have cubic, so polynomial, like this will be like cubic equations, but they will be cubic polynomial functional equations of like 2 variables, each function depending on 2 and Yang-Baxter on 3. So it's hopeless if you don't know something else. Like it's very hard to just come here and try to find. So this is not how people do. There are some methods. I will let me refer to 2. So this is by far the most successful one. So this algebraic method, and it's very simple. So once you understand it, and then it has to do with the quantum groups and like all this Baxterization and all these things that. But you can really, if you know with symmetry to expect, you can construct models in a very systematic way associated to each of the algebras. So there are very nice classifications for these cases, and you can really do a lot. And it's very simple. At the end, you are solving a linear equation to find to apply this method. Basically, it's super nice. The problem is that you only can apply when you know some kind of symmetry. You cannot apply like. You need to know like a bit what to expect in some sense. So this is most of the models that are known in the literature are found like this. This is absolutely nice. The only problem is that if you want something a bit out of these symmetries, you cannot apply it. So so it's not complete. It's very nice, simple to apply and very successful. But I think we basically found almost everything we could with it. We meaning the community, not me. Like all these classifications of trigonometric, elliptic, and rational, like associated to this algebras, were doing it like that. And so another one is something very close to what I said people don't do, which is basically try to solve Yang-Baxter directly, but you apply a derivative on it with respect to one of the variables, and then you solve the differential equations you get. This is still very bad, and it's very bad in the sense that it's the opposite of here. Here was very easy to apply, but you could get a limited amount of models. Here you can in principle apply, like in theory you can apply to any system. You can start with any ansatz and do the calculation. The problem here is technical, like you not manage to solve the differential equations. Things get bad very fast. So this was successfully applied for difference form models, basically, and a specific class of them, like, and it's very nice. They classified like all the 4x4 difference form, for example, and it's good. It's just and it's complete. In principle, can apply, but it's just very hard to apply. So what I would like to show you today is a way to do it that we will need these at the very end, but we will do many things before that will make our life lots easier. When you reach the point of doing this, you know so much information that the things you have to solve are much easier. So that's what I would like to try to convince you. And as I said here, like each of these methods had a a good thing and a bad thing. Our also will have, and the problem with ours will be that we will generate lots of dependent solutions. So we'll find so many solutions and very few are independent because there are lots of freedom of like things you can do in the R-matrix that keep Yang-Baxter invariant. So we will find lots of dependent solutions that we'll have to see somehow how if they are independent or not. This will be the downside of our method. The good thing about it is that we can do this kind of thing for many more models. So we can start with some ansatz and get many new models with much less trouble than you get here. And we can apply for different non-difference form much more easily. So that's the positive part. Okay, so we want to solve this equation. Are there any questions? Because then otherwise I'll explain a bit how the method works. Okay, so Yang-Baxter. So this was proposed for difference form first before Chiara and I entered on the group, and then by Marius, Anton, and Paul in 2019. And then after we entered on the group, we helped it to generalize for non-difference form. Okay, so the initial idea is, okay, we start with some ansatz for the Hamiltonian. And for example, let's say we just get these 8 vertex. This is just an example. I will explain later for which case we applied, but this is just some to exemplify what I mean. So we just start with some ansatz, whatever you want. And we know that if a model is integrable, it has to satisfy that all the charges commute. So a good start would be to Q2 with Q3 commute. Well, but I told before that usually to get the charges, you usually use the R. We don't know the R yet. So what we do here is we use an object it's known as the boost operator. And it's nice. So the boost operator depends only on the Hamiltonian. There's some derivative here. And the good thing about it is that it gives you the charges in a recursive way. And this was proved and defined for regular R-matrices. This is the limitation I said before, that we only could classify models that were regular. It's because of these. We are using this object to generate charges, but this object, like this, is well defined for regular only. Okay, so we know that Q2 is the Hamiltonian, so it's our ansatz. We use this to find Q3. So we put Q2 here, we use the boost, commute both, and get Q3.
What is B, Q2? What is B?
Here, it's the boost operator. It was
This
something.
one. Okay.
So yeah, this was constructed from like the transfer matrix kind of. You put things there, and they kind of managed to define this object, but it was, in principle, was defined for infinite chain only, not for finite. We are using for periodic. But the point is that in principle, it goes from minus infinity to infinity, this sum. But when you put here, like objects acting on sites that are different commute. So all the terms that don't contribute to the chain, they are 0 because they commute automatically with Q2. So it restricts exactly to the set we are. So despite that object not being itself well-defined, the commutation is well-defined. So we managed to use it to periodic chain. And then, okay, we could be worried, but at the end, you can always check that the R-matrices are correct, and they are. So it's kind of a...
Sorry, I didn't understand how you can use it for a periodic chain. I mean, you just take sum from minus infinity to infinity, or do you in that case, do you just restrict?
No, you don't need to. Look. In principle, this object is defining from minus infinity to infinity.
But H is periodic, H of n and n plus 1. The n and n plus 1 are nearest neighbors.
No, these are nearest neighbors, yes. So in principle, you define, okay, 1, 2, plus 2, 3, plus 4, 5, all the way up to infinity. But it doesn't matter because like the Hamiltonian itself, we are considering periodic. So even if this object, if this object, so let me write.
Sorry, it looks like it should diverge, but maybe it doesn't.
No, it doesn't. It's very nice actually. Like it look, if you have let's say your Hamiltonian is 4 sides only, so you have A12 plus A23 plus H34 plus H41 periodic. This object, okay, you have the derivative. Let's ignore the derivative by now and consider just this is 1 times 1, 2 plus 2 times 2, 3, and you keep going. And then you have, I don't know, 4, 5, with some coefficients here. But you take this commutator. When you take the commutator, okay, let me put one more here. Everything
but my problem is that when I get back to H12 again, it will have another coefficient.
Oh no, but yeah, you have to. Usually, you do if you do properly with indices and use periodicity, it rearranges in a nice way, and all the coefficients cancel in a way that gives you exactly. But like so, do you see that these commutes with everyone here? These also commutes with everyone here. So everything that's bigger than 4, 5, and 4, 5 we define as 4, 1, but like everything that's bigger than the size of the chain you chose commutes because they are inside different sides. So for example, each H6, 7 is, you have 5 identities here cross H. If you have but H, I don't know, 1, 2 is identity. Oops, no, it's, sorry. This is H. So these objects commute because they are identity everywhere except in except in those sides. So the point is that everything that we don't want end up being 0 automatically because of the commutator. So the commutator is well defined, even if the object, even if this boost in principle is defined to up to infinity, all the terms that don't matter, they cancel. So usually the way we do the calculation is it's instead of putting things explicitly like this, is much easier to do, and you see immediately how things work if you do in with the indices. So if you do something like the boost will be something like oops, this doesn't work very well. So you have so in principle it's this, and the Hamiltonian is I don't know, some up to the number of sides. Let's say 4, just so we don't. So because this is the Hamiltonian, this is Q for us, it will be Q R equals to 2, so we Q2. And then we know that this commutator is only not 0 when n. So we put the sum out when n is I plus 1, because then we have H I minus. When n is I minus 1, you have this, which is not 0. Then in principle you have I, but I will be 0 as well, because it's the commutator with itself. Plus I plus 1 plus 2. So let me see, EI, yeah. So these are the only terms contributing because all the rest gives the commutator 0. So it doesn't matter. You have all these other elements. All the rest gives 0. So you rearrange, and then you use periodicity to kill these coefficients in front. So this is 0 automatically. Yeah, and you get something very restricted and nice. So It's just because the commutator, like just properties of tensor products, the kind of all the commutators of things that are higher give 0 automatically, so they are killed automatically. I don't know if I confused more or was clear.
Yeah, no, it's that I hadn't understood how you were defining B of Q2. It's in a much larger space than I had understood it.
Oh, I see. Oh, yeah, okay. Okay, I see. Yeah, so things rearrange nicely in a way that only this remains, basically, because all the coefficients cancel. And so you can define Q3 like very simple. And then the difference of a difference form model and a non-difference form model appears very well here, because as we said, the difference form model, the Hamiltonian will be constant. So this term is gone. It's not here. If it's non-difference form, then we have to keep this derivative. So that's the main difference. When they introduced the method, that first they did for difference form, so they didn't have this term. And yeah, so okay, now we have Q3 and Q2, and both depending only on that ansatz we had at the beginning. So, and then we require them to commute. When we do this, when we require them to commute, what we get is, so if it was difference form, the Hamiltonian was constant. So it doesn't depend on theta here. And that derivative term was gone. It's just cubic polynomials. You just have to solve a big system of cubic polynomials. And you know which Hamiltonians will satisfy this equation or not. And if it's non-difference form, you have this derivative, so then you have to solve some ODEs instead of just cubic polynomials. You have to solve some ODEs on these variables we proposed at the beginning. And if you do these, there are many, since it's a system of equations and cubic equations, you get more than one solution. You have all like some set of solutions. And we say that they are potentially integrable Hamiltonians. And the potentially, it's because if you want integrability, you need all the charges to commute, not only the first two. So we need to find the R somehow, because there is no way we can do all the infinite charges in this way. Like we need to, and the good news is that Q2 and Q3 fix not only enough to allow you to do the calculation, but it fixes completely the Hamiltonian. So at least for all the models we found so far, all the new models and the known ones that we just recovered, this was enough. We never found extra conditions on the Hamiltonian. The Hamiltonian was, and then we discovered in the literature some conjecture by Rashetikin, where he discusses these actually, and he has a conjecture that this should be enough, but there are no proofs for the conjecture. We found that we tried a lot to prove it, didn't manage, but we found all the models are satisfying the conjecture. So far we are finding that the conjecture is fine. So this seems to be to fix enough the Hamiltonian. So what I mean, okay, so we solved these, we have these potentially integrable Hamiltonians, and then we try to find the R for each of them. And now, by solving the Yang-Baxter equation in the sense I mentioned before, that you apply the derivative, but we need the boundary conditions to be satisfied. So we need that R becomes B and the Hamiltonian is generated. So these are our boundary conditions. If you derivate Yang-Baxter and you put those conditions here, you get what it's a version of Sutherland equation. It looks like this. So, but now we know the Hamiltonian. Before you had a system of like coupled equations, and you didn't know anything. You had three R's. Like the advantage of this is that we restricted the Hamiltonian enough that it becomes much easier to solve this equation. So that's the biggest advantage. And then you can go So we still will not be able to solve like a matrix with all unknowns, like if you take the especially the non-difference form, but we can do a lot. Like actually, it's quite nice. I'm quite excited about this because you can solve many, you can find many models. So you just substitute each of those Hamiltonians you found that were potentially integrable, and you solve for R. Every time we found a case that we had a Hamiltonian that was potentially integrable, it was integrable at the end. We didn't find any extra condition on H. If you put what you had there here, you solve for the R's. You don't need to find you don't need to put extra conditions on the H. This is completely fixed by Q2, Q3 apparently for the models we found. So you solve this with these boundary conditions. And it's just a system of PDEs that can be easier or harder depending how many non-zero elements you put in your ansatz at the beginning. And then you find an R and you check for Yang-Baxter. So I realized it was like maybe confusing. So let me summarize and repeat what's the method, the whole method. You start with some ansatz, some general, as general as you want, or you are hopeful to solve. If it's too bad, it becomes harder. But you start with some general ansatz. You use the boost operator to generate Q3. And then as I showed, like this is like a closed formula for Q3. So once you found it, you just can keep using. And then you require Q2 with Q3 commute. You solve the polynomial or differential equation, depending on what you want. You find some Hamiltonians that in principle are integrable, but you don't know because you still need to compute all the other charges. You solve Yang-Baxter with these boundary conditions, and you find an R-matrix. And then you put on Yang-Baxter back. If it's okay, you did everything correct. And then you don't need to find all the other charges, or because if you have R-matrix, you automatically have all the other charges by a completely different way to compute them. Like this is a very well-defined thing. And once you have the R-matrix.
So if I understood you correctly, in this last step, you solved the Sutherland equation, was it?
Yes, yes.
Just that, and that's sufficient to give you the R-matrix.
Yeah,
you verify that it satisfies Yang-Baxter.
Yes, because since it's the derivative of Yang-Baxter with some, you cannot be completely sure that it will satisfy the original one. The fact that it satisfies the derivative doesn't mean in principle that it satisfies the original equation. So we always check it then to see if and it always did. So every case so far, I think, we have like maybe 20 new models. All of them were in, I don't know, it really works well. We are, I don't know, we are very happy because to have to solve Q2 with Q3 only, it's quite nice. You don't need to, it helps so much to do the last step. Like, so that's basically the method. Then my idea was to now show some of the new models and some of the consequences of the, how much time do I have? Sorry.
We are relaxed about time as long as people are still interested. It's recorded. If people need to go, they can catch the end of it.
Okay, yeah. Okay, so we thought in trying to do a 16 by 16 case, like so a vector space of dimension 4. Hubbard is in these, is in like this size basically. But like to do in general is still too much for us because you have 256 components, and then if you do these, the problem is even if you manage to solve the cubic coupled cubic polynomial equations. Oh, this is difference form, by the way. This first example will be difference form. So the Hamiltonian is constant. No derivatives no differential equations to solve in the Q2, Q3 step. It's just a set, like some set of cubic polynomial equations to solve in Mathematica. But this is too big. If you have 256 unknowns, even if you manage to make Mathematica solve, you will generate so many dependent solutions that will never manage to see which ones are independent. Like it gets too out of control. So we wanted to do something like as the first thing, like to do something that was, we had control enough. And also we expected to find some interesting models. So we knew that SU2 plus SU2 already has, so SU2 plus SU2 graded has Hubbard there, for example. This is a bit simpler because Hubbard is non-difference form. So this is simpler than Hubbard, but we expected to find something physically interesting here. So this was our first, we thought like it was a good laboratory to study.
What is the meaning of independent?
Oh, yes. So I put it then here. Let me.
It's not a linear system, so I don't understand.
Yes. So I put here. So if there was after the. So the point is that Yang-Baxter, it's invariant. If you do normalization, for example, if you take R and send to some G times R, some function, and then this is the consequence of the Hamiltonian. So this doesn't change Yang-Baxter because you just get an overall factor in both sides that cancel, right? So this keeps in, so solutions that are related by an overall normalization, we consider the same. Okay, this is easy to check, right? If they are this, if they are the same. So two solutions that are related for an overall function for us is they are dependent on each other. They are not independent.
Okay, one more question. What is the Hamiltonian on a single particle? I mean, H12, H on the 2, V cross V. But one needs, at least quantum mechanics, one needs a single particle Hamiltonian. What is it?
Oh, no, but we are considering always, the Hamiltonian for us always acts on 2. So these regularity things means we have a Hamiltonian that acts on nearest neighbor. So all the models we are considering here, they are always Hamiltonian who acts on, each density Hamiltonian acts on 2 particles.
So one cannot define energy of a single particle or anything like that. I mean,
then you have to think, you can think as then, for example, you can think as pseudo particles moving in the chain, these kind of things. Yes, you can define the dispersion relations and energies and things, but yeah, like for example, if you have like something with all spins up except one that's down, you can think of like as magnons, and like you can think as a pseudo particle moving in the chain. And in this sense, yes, you can define the energy of one particle.
So my issue is that once you have in some way something acting on V, then one needs a co-product to define what it does on V cross V. There are consistency conditions, okay, which leads normally to the Yang-Baxter equations.
Yeah, I know you can.
Don't seem to have it, yeah?
Yeah, but to define a co-product, usually you have to have some algebra in mind. You not necessarily like.
But if you want to do some physics, one needs an algebra, no? Some observable.
So yes, but like.
For example, in the Hubbard model, there are spins sitting at each side, and there are operators acting on it.
Yes, I will talk about something like that soon, but I don't know if I understood well what because you were. Yes, because we are starting already with the Hamiltonian that acts on, like the density Hamiltonians for us act only on at the minimum, like not on the minimum. They always act for this method and everything they are doing. They act always in 2 sides, the density Hamiltonian. So
okay,
we cannot like it not even applies if this is not true. Like so, everything we are doing, it's like that. But I can see what you mean in the sense that you have particles in each side. It's just that I think to compute the energy in that sense, you can do it with that ansatz, but then you are thinking in terms of excitations, not so depending on which type of excitation you have the energies and the so.
No, once you are given operators on V, then
yes.
there are co-products which are required to be.
I agree.
So I don't see them. I don't see how you are defining them. So one does not have a half algebra, or even.
No, I'm not defining because for the method, we didn't need them. Like usually, because like you were thinking in a way similar to the way like Fadiev and all these in this first method people did. And that's very useful, but you need some algebra and some symmetry associated to. We wanted to go a bit out of that.
Okay. It is not very clear to me how to do physics with this, as of because of a lack of this co-product. I don't know how to formulate, for example, the Zamolodchikov model, okay, where you need some scattering of individual particles. I don't see how to formulate it.
Well, I think the Hamiltonian of this system, of the entire system, is the sum over these pairwise Hamiltonians.
Yes.
These are the Hamiltonians that are acting on nearest neighbor sites.
Yeah, so each density acts on two sides, but the total one will be a sum.
And the collective Hamiltonian is the sum over all of them.
Yes.
So, and that's the object whose eigenvalues you would look for. And those would be the
yes.
energy excitations of the entire system.
Yes, exactly.
So this is a many-body system.
Yes.
From a physics point of view.
Yes, exactly. And yeah, so in the sense of which solutions are independent, also, it's just that there are many transformations you can do in R that keep Yang-Baxter invariant. That's basically what I mean. Like you can do basis transformation, reparametrizations, some discrete transformations using P and transposition. So all these keep Yang-Baxter invariant. So our method generates lots of dependent ones, and then you have to see which ones are, because all these four, for example, keep the spectrum invariant. Like you don't change your degeneracies or anything. So they are the same model physically. So we don't want to give them 10 times on the paper or because they are the same model. So we have to distinguish them. So if we try to solve something too big, you end up having so many dependent ones that you are in trouble. So that's what I meant before.
Ricardo has a question.
Yes, he asked about Jacobi. I was waiting for, yeah. But I don't see any relation of Jacobi here in classical integrability. In classical,
I thought the question was too naive to interrupt you.
Oh no, that's it's
in a way what I see is sorry, I'm ignorant
no.
the subject matter, but it seemed like an integrability condition that you need to have integrable system. Sorry for the redundancy. And taking advantage that there are some experts in the audience on group theory, how that comes in, because honestly, in perhaps this is a question better for later. I don't know, what's the input, what's the output of this Yang-Baxter equation? I don't understand. From what I see from a slide, I have an R-matrix, that gives me charges, and then I see charges that give me, I don't know what's.
Oh, it's because, okay, so if you have the R, in the usual way, if you have the R-matrix, you can get the charges with a very systematic method, but you also can get the spectrum, you can solve the model in general.
But you're obtaining the R-matrix
from the charges, but this is not usual, it's another, so we are finding R's that are not known. We are just reverse engineering in some sense, because we found the Hamiltonian. So we usually, okay, there were some ways to do it, but the point is that once you know the R, once somebody gave you a solution of Yang-Baxter, you can get the charges in whatever you need with them. The point is that here we just don't know them yet, and we were finding a way to, so
Because even the Hamiltonian you wrote was H equal P R dot. I don't know many Hamiltonians that factorize that way.
Yeah, they
It's
are.
something like putting a very restrictive condition from the beginning of the game.
It is, but I see your point. But when you have
it's like putting integrability from the outset.
That's exactly what she wants to do.
Can I report? There is one question that Ricardo asked, which is about the Jacobi identity. Okay.
yeah,
So,
like
at least what I know is that one starts with the Lie algebra acting on V, not V cross V, and it is an algebra. It's the commutations are defined, and one defines the coproduct of the Lie algebra into V cross V, delta of some element of the Lie algebra in V cross V, and it is required to fulfill the same algebraic relations. So that defines the coproduct, which in the simplest case is L goes in L cross 1 plus 1 cross L. But in the general case, it is. So the Jacobi identity is encoded in the coproduct. That's what does at least bothering me.
I agree with these. It's just that I think you are thinking in it's a correct and it's a very important way to think about. It's the and I think it's the way lots of people, like all these known models that are known for a long time were constructed. I agree with you. It's just that,
if I might comment, for me, the essence is closer to the two-dimensionalizing model and the star triangle relation, which is the origin of Baxter's work.
Yeah. So
in that setting, the Hamiltonian is the Ising Hamiltonian.
Yes. Can I make one more remark?
it's just that.
Sorry, may I interrupt? The
Yes,
way
yes.
I understood, the way
Yes.
Yang-Baxter emerges is one step. I mean, to at least to my understanding, or the Leningrad school, you start from a dynamical system on a Hilbert space, which we call V. Okay, so there
Yes.
are operators acting on it, and one wants to compose this system. Say two particles. How does it act on V cross V? So there's a coproduct on the algebra, which is a representation of A. So A goes to delta A. Okay, the commutant of delta A is what gives the braid group. Okay, for example, the simplest case, it gives a permutation group, but the braid group, if you add to the elements, I think Pramod will agree, the flip operator, one gets the Yang-Baxter. Okay? This is what you call P, I think, the flip operator operating.
The one.
So
Yeah.
there is a physical thing going on here, and here I don't see. It looks like, to me, it looks like starting in the middle. I won't know how to do physics with this.
Yeah, but I like. Do you agree that okay, you have an object that so okay, wait. Once you have the Hamiltonian and you know it's integrable, or like okay, you can have the Hamiltonian or any of the charges, you can start to study it. For example, you can really think in spaces like putting particles like so. For example, we found some models here like these SU2 plus SU2 ones, and you can think as really so. Let me show this example, and then I can say a few things about the Hamiltonian and how you can see it physically. But this 8, 9, 10 I separated exactly because they had some obvious kind of nice physical thing going on, which is that they have this GHKL0. So if you look at what GHKL, so these are the classes that are SU2 plus SU2. So phi's are the bosonic ones, so are the one without any particle, or with two particles, one up and one down, and the psi's are the fermionic state, so with only one electron or up or down. So if you have GHKL, it means that when your Hamiltonian acts on two, so when it acts on states that have, for example, so you have no particle here, for example, on the phi, and one particle here, it gives you 0. So if particles are alone in this chain, they just don't move. So we found this, like, for example, if you see 5 particles, you have this Hamiltonian. And if you have a 5 psi, it's basically you act with the Hamiltonian, you get the eigenvalue. Nothing changes, nothing happens, because this type of, the particle just stays there. So we need at least two electrons together to move. So these 3 models we found, they have this nice, so it has physical, you can study physical things in some sense. I don't know if I'm replying what, because I know like you are thinking in the original way that people did, and I agree that all that makes sense, but you also can just take Yang-Baxter as an equation to solve, and the things you get, they still make sense. You can still study them, even if you don't have a, like in principle algebra or something associated. You can, and then you still have the higher charges. I agree with you that can be hard to study symmetries. There are many models that we found that we don't know which symmetries they have in addition to the original one we put. These 2 models, this model is an example, for example, like if you, so yeah, if you have 2 electrons, they can move. But like if you take these 3 models, they are very different. They all have SU2 plus SU2, but if these are the degeneracies for 4 sides. There are 3 models. The 3 have this behavior of the electrons alone cannot move. They need to be in pairs to move on the chain when you act with the Hamiltonian. But they are very different. The 3 of them have SU2 plus SU2, but they have much more symmetry, and we don't know. If you kind of know, if you can write the coproducts and things in the way you are thinking, it's very nice because you can already say a lot about the symmetry. The fact that we don't necessarily have that from the way we did, it puts this challenge of interpret these as, but you still can study the models and say many things about the physics. I don't know if
I think you were going to show us a little bit more detail on some of the models.
Okay.
It would be helpful to see that, Anna.
Oh,
We have sidetracked you and you've jumped ahead a lot.
Yeah, no, but I didn't put, for example, batons at here or anything, so I didn't put on the slides.
No, that's okay. Yeah.
Yeah, so this is just.
Can I ask? I'm
Yes.
sorry to interrupt again. Sorry to interrupt.
No.
Can I ask about? I'm still not understanding how you find the R matrix, because as you keep saying, you're doing some process of like reverse engineering. So you start with you already start with the nearest neighbor Hamiltonian, and then you construct the charges, and then from that you solve some differential equation and find the R matrix. Is that right?
Yes.
Okay. So what are the assumptions that you make when you choose this Hamiltonian? Are you allowed to choose any kind of nearest neighbor Hamiltonian?
Yeah, you start with depends on. So the first thing you have to decide is like what's the size of the Hilbert space you want to work with. So if you, for example, you want I don't know, Hilbert space dimension 2, so you have a 4x4 R because R acts in 2 spaces. You have and a Hamiltonian that's so your density Hamiltonian will be 4x4, and then you have to decide how many non-zeros you want to put. As crowd, like if it's too crowded, it's harder to apply the method. But you can have many non-zeros. So if you have something like of dimension, Hilbert space of dimension 4, so the Hamiltonian is 16 by 16 like we did. Here we consider a case with, it's only 10 unknowns. So we have many non-zeros, but some are repeated because of SU2 plus SU2. So this was a choice, like as more elements non-zero you put, harder it is to solve, but there's no restriction besides like any nearest neighbor. In principle, you can apply the method. It just gets technically more and more difficult if you put more unknowns on it, more like So one thing you can do, for example, is try to discover if your Hamiltonian is integrable or not. You have a Hamiltonian with very specific coefficients. In principle, we can try to say if it satisfies Q2 with Q3. We can construct the boost with that and do and say something about the integrability of that Hamiltonian just with this boost construction. But
so, and if I take a two-dimensional Hilbert space, what do we get?
Two-dimensional Hilbert space, 4x4. So yeah, they
and our matrix is 4x4. That's presumably much easier to solve. What family of models come out of that?
If it's difference form, Marius, Anton, and Paul, they did that in the paper. They introduced these. They classified and they found all the usual models, XXX, all the usual ones, and plus I think 5 or 6 classes of models, but they are very particular in some sense. They don't have much symmetry, and they did a complete classifications of all the 16 by 16, all the 16 elements, non-zero.
Yes, but and what is the simplest model that comes out of that? Just to set it in a concrete setting, it would probably help to answer Per Randven's
4 or 5
question.
5, I think, non-zero elements only. The simplest one, it's very simple. Like you can get, of course, you can get some like identity or like it's something that works, but you can. They got 2 or 3 nilpotent models. And things, so you can get things very simple like nilpotency or things that so you get many. It was one of the reasons when we were discussing like that also Marius wanted to do this SU2 plus SU2 because if you do general one, not necessarily all the solutions you find are useful because some are so simple or so particular that you cannot do much physically with them. So yeah, like I think, the simplest I think is like identity, but
that's a little too trivial.
But you have some that are or just upper diagonal, nothing on the lower. These kind of things you get. Yes.
Okay. Sorry, Pramod wanted to ask again.
Yes. So I am actually so the impression being made is that if I start with any nearest neighbor like Hamiltonian, I can always find an R matrix for that. But I think it's oversimplified. No, this is not true for any nearest neighbor Hamiltonian.
Hamiltonian that will give you an R. Because what you get is that you put some ansatz and then you find conditions on those matrix elements in order to that be integrable. So it's probably correct if you start with something general enough, you always find an R. And many times you find many. For example, we found for this SU2 plus SU2, we found 12 different independent models. 6 of them were new. You can always.
No, I'm not understanding that part because you're only doing 2 charges, right? You're only taking Q2, which is your Hamiltonian, which you're going to choose. So Q2 is chosen, and Q3 is the ansatz, right? Q3 is the ansatz. No. So how do you know that you will get an infinite power of charges after that?
Oh, because you found R. We found R. We solved the Yang-Baxter. Once you have Yang-Baxter, you have a way to generate all the charges automatically.
Yeah. So of course, if you have the R matrix, I agree, but I just don't understand, like if you just use Q3 and Q2, you'll get the R. That seems a bit simplified.
I think the statement is that Q2 is not specified until it satisfies the equations.
Yeah, Q2 is an ansatz. So you start to, for example, let's just an example. If you start with, you can start with these ansatz, but if you see Q3 in the way it was constructed, it's completely defined in terms of that H. So that H, you still don't know the matrix elements there, but Q3 is also in terms of matrix elements. So this equation, it basically relates all your unknowns inside, like your first object was the ansatz Hamiltonian. You are just fixing this Hamiltonian. The Hamiltonian is the only unknown. So the elements of the Hamiltonian is the only unknown in this equation is that you solve for it.
Yeah. Okay. And
then you get
from this you get. From this, how do you get the R matrix?
So from this you get the Hamiltonian, And then
Okay.
you apply the derivative. If you apply the derivative on Yang-Baxter, you get this Sutherland. And if you put those boundary conditions here, you have the Hamiltonian here. So now you have an equation for R. And,
Okay, I see.
and in principle, you fix it the Hamiltonian, not completely, but sorry, but you fix it completely, but we don't know why Q3 is enough. There was a conjecture about these apparently already, but we couldn't prove yet. And Rashetikhin didn't, it just put as a conjecture many years ago. So I don't know. It looks like so far it's enough. Q3 fixed the Hamiltonian enough. And then when you solve this equation, you don't get any extra condition on the Hamiltonian. You just get the R. You don't need to.
I see. Okay.
Actually, 2 times we thought we needed 2 conditions, more conditions on the Hamiltonian, but it was always we making mistakes on mathematics. And then we end
Okay.
up,
So one final question on this. So are you reducing the complexity? So if you try to solve for the R matrix straight away, like without doing this method, you have some complexity, right? For all your equations. So if you do this alternative way, are you going to reduce that complexity, and is it going to become easier to find
yeah,
the
like
R
if
matrix
you do
with this?
these, yeah, it saves a lot of effort and time, because since you already reduce the Hamiltonian to the one, like, because if you apply the derivative on Yang-Baxter without knowing the Hamiltonian, you have too many things to solve for. You have the R, the equations very coupled, or you have a very coupled equations for R, or if you assume that this is true anyway and put here, so you have all unknowns in H and all unknowns in R. So you kind of just don't have anything to, it's too many unknown to, it's very hard. People did this for some cases, but it's very hard. So here you reduce a lot the complexity by doing this step first and fixing the Hamiltonian.
Okay.
I don't know
Okay,
if
thanks.
Yeah.
Yeah, I think it makes sense. Okay.
Very good. Very good. Yeah, please continue from. We would like to see some of your the introduction to your models. This is very good. Yeah, please. Here is the previous one. This one we didn't get. Okay.
Yeah. So the idea was that it's too complicated to do general. So we did SU2 plus SU2 to start. And so here you think the bosonic states as empty or 2 particles, like so you have like a site with nothing, or a site with where you created a particle with spin up and 1 down. So this is phi 2, and then psi 1 and psi 2 are you create as like an electron like a particle with spin up and one with spin down, and then we put in a periodic chain. So each site can have one of these 4 configurations. And if you require that it has SU2 plus SU2 symmetry, it restricts to this. You have that the Hamiltonian acts on phi, gives you this. So it gives you phi back, the one with opposite order, plus the psi. If you act on like a 5 psi, you get 5 psi plus psi phi. And so you have, these are the possibilities you have. If you want SU2 plus SU2, the Hamiltonian can, and then you can put these on a matrix and see how it looks in a matrix. But it's these are the allowed operations you can do with your Hamiltonian if you want SU2 plus SU2. So you have 10 unknowns here. And then we apply the method. I will not repeat the method, but yeah. And then we found 12 independent solutions. And then among these, there are kind of classes here. So some are like just an embedding of XXX. Some are, so the last one is Hubbard, but free Hubbard. Only the kinetic part of Hubbard is integrable by itself, because this is difference form. So Hubbard's not here. We did the after non-difference form, and then Hubbard is there, but it's not here. So 6 of these models were known and 6 were new. And then this 8, 9, 10 we are quite curious to do Bethe-Ansatz. We didn't do yet, but we are quite curious to solve them and find and see what, because yeah, as I was saying, like they have this GHKL equal to 0. So if you have one particle in your chain, so if you have like phi1 psi, for example, and since these are 0 for this model, like the Hamiltonian.
So they have only bosonic or fermionic states. There's no fermionic states, I think, actually, is what it means.
Yeah, it kind of, if you have,
it's only the even states that are present.
So if you have like fermionic states, like this example, for example, like if you have a 5 sides and then you have a phi1, psi1, phi1, psi2, phi1. So if you have like something that, so this is empty, right? It's like a no particle. This has one particle of spin up and this is one down. So you have like just one electron alone in the chain. It will stay there for like, this is just an eigenstate of your Hamiltonian. It doesn't, but if you have something like two psis in a row that you have two psi, so if you have like psi, then you have like two particles in neighbor sides, then they move because psi, it's here, like you have something. But and if you had like a phi1, phi2, you had you have two particles on one side, they also move because then it satisfies this one. The problem it's every time you have something like this, it's just an eigenstate of your Hamiltonian. It just doesn't move at all. It just those. So I think this is responsible for the huge degeneracies that are there because. But so I don't know.
I think this answers your question, Val, about what is moving. You can see that you can take e to the I times a, the Hamiltonian, and it will evolve some of those states. They'll just move around the lattice.
So let me ask, I have to think about this. But is it obvious that this H is self-adjoint? Because it looks triangular. I mean, it doesn't look, so is it self-adjoint?
Are you worried about hermiticity and these things?
No, you have defined H on the two particle sector, which is a Hilbert space.
Yes.
So is this H a self-adjoint operator as defined? What are the conditions on these coefficients to have a self-adjointness?
Oh. Didn't think. I just
the other side.
I checked that, for example, model 8 has complex eigenvalues and it's not a Hermitian, and model 9 and 10 are Hermitian. More than that, I didn't.
Next slide, you had an equation with H acting on all the two-body states. This equation, yes. Top 4 lines. Does it define H as a self-adjoint operator on the two-particle sector?
I don't know. I didn't.
Okay.
Expect.
It doesn't look, it looks triangular. That is, it looks like a Jordan matrix.
Yeah, I don't think it looks self-adjoint. I mean, actually, it is not enough. Like, so the R matrix has to satisfy some more conditions if you want to apply the algebraic Bethe-Ansatz. So you should also have like crossing symmetry, for example, if you want to apply algebraic Bethe-Ansatz.
Oh, that's true. Yeah, this has braiding unitarity. All of the models we found so far we never asked it for, but they have braiding unitarity, but many of them don't have crossing. So but we didn't apply Bethe-Ansatz for any model. So yeah, I don't think this one is crossing symmetric. At least I'm pretty sure model 8 is not. 9 and 10 I have to look. So if I'm honest, we are still like looking the models, like we didn't study much of the physics of we found many models and now we have to look all of them kind of what they mean, because we spend lots of time trying to see which ones were independent and these things, but we don't know yet much of the physics about them. Like we just know that so these three kind of behave in the same way of these with this 0 here. And but they have very different degeneracies. And these two seem to be physical in the sense that they have they are the Hamiltonian intermission, but this is not. But I agree that I don't think we have crossing on this one. Yeah. Yeah, this is the form of the R for them. Sorry, it's already 1 hour and a half. Is it okay? Should I say
That's okay. We're asking our questions as we go along.
Okay. Okay. Yeah, I think I have to go at 4:15 if it's not.
Okay, that's fine.
But
if you want to continue and just try and wrap it up, so in some whatever way it suits you best, so we can, if you have to go in 10 minutes or something.
Okay. Okay. So like I don't know if I talk about these or ADS. Okay, as I said, the kinetic part of Hubbard is integrable separately. Even like the full one is integrable, of course, but just the kinetic part is integrable. And then we started to add things, like we wanted to see what we could add. Okay, we will break SU2 plus SU2, but we wanted to see what we could interpret as electrons moving in a chain that we could add on this. So we wanted some only things that preserve fermion number. So we added these K pairs that they move one pair from one side to the next. So you kind of destroy a particle of spin down and up in the side 1 and create a spin on the side 2, or the other way around. And we added these K flips that for example, you can destroy 2 particles of spin up and create 2 down instead, or etc. And these don't preserve fermion number because you can destroy like 2 up and create 2 down instead of something. And then we added some potential, and then we had all the potential we could think that made sense. And then we assumed this Hamiltonian. It had 2 and 2 free parameters, and we asked it if it's integrable, what conditions we have. And then we found only one non-trivial model. It's this. And you it doesn't conserve spin orientation, but it has two parameters here. It has A and B. So in principle, it could have some phase transition or something. So this looked nice, but this for sure doesn't have Bethe-Ansatz because it doesn't satisfy spin orientation. So it's like XYZ. You need some alternative. You cannot do, but it looked interesting for us. So this is a new model. But if you add, so all the things you could add that preserve fermion number, only this one is integrable. So only one of you only find one model. And then yeah, I think this is too confusing to say in 5 minutes. I think I will jump for the. So we try to apply these to find the formations of ADS 3 and 2. So these are 4x4 models, but they are each block is like 4x4, and we try to use and then it's non-difference form, so it's not the same cases that Marius classified with the group. So we classified these with them, and we found kind of 3 deformations. And one is quite surprising, which is this one. We found kind of an 8 vertex deformation of ADS3. ADS3, if you know a little bit, it's like 6 vertex, the blocks, not 8. And so I think this is the first 8 vertex or elliptic deformation of ADS3 in this sense. So we are very curious about the consequences of these, but I think I will jump for the conclusions because yeah, this is a bit too confusing to say, too short, too fast. But the point is that one of the models we found in different limits go to ADS3 or ADS2. Like you can recover one or the other by taking the modulus of the Jacobi function to infinity or to 0. So it's kind of nice. This part was completely unexpected. So I was excited to. But summarizing, so presented a new method to construct the R-matrices that we to construct new R-matrices satisfying Yang-Baxter, and some models have potentially interesting physical properties, but honestly, we studied very little them for now. So everything to be studied on the models. We basically found them only, and we also found 3 deformations of ADS. And then there are lots of things that one could do. You could consider less symmetry. So we put this SU2 plus SU2 or these 8 vertex to solve the ADS cases. But you can do a lot, actually, a lot more. Like you could put many more non-zeros in these matrices and try to find new integrable models. So a much more general classification could be done. You of course cannot do all non-zeros in the matrices, but you can put many more non-zeros and find. So yeah, and then I had put these, but now I agree I have to check about crossing symmetry. So maybe you not even can do Betons. That's there. You have to find an alternative. But maybe I don't know, Q operators or something could work. I don't know. Yeah, this deformed Hubbard-like model, that in principle is interesting. And then yeah, we are very curious about these deformations of ADS, if there is some sigma model associated, if they really come from some string theory, or if they are just some deformation that doesn't mean. So we don't know yet what does they mean. Do they mean? And I think these questions remains, and it's like, why Q2 with Q3 is enough? Why it fixes everything? The conjecture is not true, like we wanted a counterexample, or we want to write the proof, but so far we didn't do any of them. We didn't manage any of the options. So thank you. And sorry, I talked for a long time.
Thank you very much. No, not at all. We've had lots of questions, as you may have noticed. So
what is the K matrix? Sorry. What is the K matrix? What is that?
Oh, it's just that we only consider periodic boundary conditions, but once you have the R, you can find the reflection matrices and study open spin chains. Once you have the R, you can open the chain and do a lot. So we didn't study which boundary conditions, or which which boundary conditions you can put in a chain that would be integrable. So once you have the R, you can classify all the K matrices. So all the boundary conditions for an open chain. You can do that systematically. That's an easy procedure. Like once you have the R, so this would be something just sit and do. It's not something that would be, in principle, incredibly hard. I don't know if there will be some practical difficulty, but in general, it's something nice and that it's well known how to do.
What is K? I mean, but what is K?
K is the reflection matrix. So if you want to have an open spin chain, you need to satisfy the Yang-Baxter, but you need to satisfy the boundary Yang-Baxter as well that relates R and K. So you have something like RK. So it basically describes what happens when you have a boundary. The K is the matrix that describes, so you have one K describing your left boundary and one K describing your right boundary. So it's a boundary matrix. I don't know.
Did you find anything beyond the matrix?
Did I found what?
You had rational solutions, metric, and elliptic. Was there anything beyond more complicated than elliptic?
I still cannot understand. I'm very sorry.
Somebody can translate. Here, the voice is, well, I think Danger can tell what Werner is asking.
I'm missing a word in it.
There is some sound together,
yeah,
right? Not only one.
It sounded like metric, but I didn't understand why metric would be the word. Can you repeat it one more time? Just maybe as slowly as you can, Werner, so that the words are separated.
You have rational, trigonometric, and elliptic. elliptic you did not show, but you had one elliptic example. Did you find anything beyond more complicated than elliptic?
Okay, I got the question at least. He wants to know, did you find anything beyond elliptic? You found trigonometric and you found elliptic. Did you find, he wants to know the form of the functions that cropped up in your solutions. You found trigonometric solutions, you found elliptic solutions. Did you find anything more exotic? Did I repeat the question correctly, Werner?
No, we didn't.
Yes.
Okay.
No, not so far. Yeah, so far when usually when we had like Hamiltonian that was trigonometric, we kind of end up with I don't know, some elliptic R, but I think yeah, I think you would have to find something like an elliptic R to get something more complicated, an elliptic H to find a more complicated. It didn't happen so far. It will be quite interesting, but we consider very particular cases so far. We didn't do anything too crazy yet, not too out of the. We didn't choose matrix elements too different because they're more or less the ones around P that you put, or like with some symmetries. We didn't do yet something that's too weird in some sense. So no. But in not weird in a bad sense, but like it's nothing out of the usual enough, I think, to because usually depending on which type of element you put, you automatically get like something elliptic, for example, like so we have more or less ideas which elements we have to put to have at least the ones that would more or less generate like something elliptic, that are the trigonometric and rational are harder to see from, but elliptic you kind of know which ones you have to put to have a chance to get them. But I don't know if you put them completely in different positions. I don't know what to expect. But yeah, the short answer is no.
So suppose if you change the X type, that X type of ansatz that you take, if you change the position of the non-zero elements, you probably will find something new, right? You should.
Yes. So yeah, but we tried a complete classification for non-difference form 4x4, but it's very hard because it's too crowded. If you the problem is not to have too many elements. Like if you take something bigger, like 16 by 16, and you put many non-zero, it's fine. Many non-zeros, it's fine. The problem is that too crowded. If there are too many, like if the percentage of the matrix that's taken is too big, that's non-zero is too big. The way the terms multiply gets much harder to solve. But I think the consequence would be exactly to get some more unusual solution, something out of the rational elliptic range. So I think you do
so I should add that the constant solutions, at least the 4x4 case, it's been fully classified.
Yes.
The full classification is there. So you could probably try to Baxterize those and see in which position they come. In which position you get the non-zero elements. And then if you try those ansatz for your H, you probably will find some more solutions.
Do you mean to take the difference form ones, see which ones generate something a bit different, and then do the same in non-difference? Just assume the same matrix elements in non-difference?
Yeah. All you need to find out is in which place you have to put the non-zero element, and then it should immediately start giving you like several solutions. So if you just know how to Baxterize all the solutions, which was written down by the Finnish guy, I don't remember the name actually. So he has all the constant 4x4 solutions, at least the 4x4. So it should be possible. I mean, So it seems like you're only trying the X. Yeah. So I know his name. His name is Hitarinta. Yeah.
Oh, so this paper I don't know, because I know that Vieira and I think Lima Santos as well.
No.
Vieira did this.
Yeah.
Uh,
They are from São Carlos, but
yes.
you have to. Yeah, but there is a much older paper by a person from Finland. It's called Hitarinta. HI. So I can type it. It's called Hitarinta. So he has all the solutions.
Oh, I didn't know that, because when I think when Marius did to check the method, and he compared with Vieira, but I should look this. Thank you very much.
Pramod is joining us from India.
Yes, I know. Yeah, okay, yeah. I know some of his papers. I didn't know this one, but yeah.
Okay.
Yeah, that's.
Thank you very much for a very interesting seminar. As you can see, it stimulated a lot of discussion. Pramod tells me he's from India. Bal, you probably know him.
I am a student of Bal.
Okay.
I was a student of Bal long ago, yeah.
Then I recognize the name. Okay, very good.
So I think Anna needs to go. Thank you so much.
Yeah,
Anna.
thank you very much.
Thank you so much. It was very nice. I really, lots of good questions. I was very happy.
Oh, actually, if you're ever in Dios, please do let me know. I have a lot of questions for you.
Yeah,
yes. I learned a lot from your talk. Thank you.
Thank you very much. And yeah, I hope
there's probably time for one last question. Is there, or you have to rush?
Yeah,
it's 4:30 the thing, so
okay, all right. Well, let's thank you very much. We will come in and visit us sometime, and we can discuss further. Okay.
Yeah, thank you very much.
Right.
Very nice.
I will end the.
Really enjoyed it. Yeah. Thank you.
Okay.
Thank you.
I'm going to end the recording, and we can be.
And have fun in Durham, but definitely.